Hello, geometry students. I hope you are all doing well. We are going into chapter 8, which is all about right triangles and trigonometry and things like that. But we need to practice a couple skills before we go into that. So we're just calling this section 8-0, and we're just going to be reviewing radicals today. So what is a radical? Basically, a radical is a square root symbol. Essentially, you're looking for this guy. This does not mean division, and it's a different symbol. Notice how it has this little, I call it an elbow. It has a little elbow in there. So that is different from a division symbol. Now, you have already seen these, and you're relatively familiar, I would imagine, with a number of types of radicals, something called a perfect square. So, a perfect square is what you're going to get when a whole number is the solution to a radical. So 36 would be a perfect square. In other words, the square root of 36 is equal to 6. Notice how a whole number is the end result of this. Or the square root of 49 is equal to 7. Another one, the square root of 100 is equal to 10. Now, what am I doing with all of these? Well, basically, I'm asking myself, what times itself gets me the inside of the radical? That's what I'm asking myself when I do these calculations. What multiplied by itself gets me the inside of the radical? So some of these are easier to do in your head than others. Some will end up being perfect squares and some not so much. So I'm going to talk to you today about how to simplify these and just in general how to work with radicals. So first of all, I have this little statement here that I'd like for you to be mindful of. How do you handle radicals? In general, we handle operations of radicals like variables. So if variables do not match, then we cannot add them. That works the same with radicals. If radicals do not match, then we cannot add them. We are allowed to multiply anything we want together when it comes to variables. Same way goes with radicals. So let's go ahead and begin just practicing some of this, and you're going to see this kind of unfold. So here, example 1 is finding prime factorization. It says simplify each term into simplest radical form. So this just means leave it as a radical if need be. Do not use decimals. So do not use decimals. So we're getting rid of that. No more calculator stuff. If it's a perfect square, then that won't be too bad. So let's just look at our first example, the square root of 100. That is a perfect square. So the square root of 100 is equal to 10. Let's go on to the next example. The square root of 108 is not a perfect square. So an easy way to work through this is to break it down into its prime numbers. The way we're going to do that is by forming a factor tree. So I have 108, and I'm just going to start breaking it down into numbers that I know multiply to 108. Well, I notice that it's even, so I'm going to say 2 times 54. 54 is also even, so I'm going to say that's 2 times 27. 27 is divisible by 3 and 9, so I'm going to say 3 times 9. And then 9 breaks down into 3 times 3. So now I have all of my prime factorization. I have 2, 2, 3, 3, and 3. What I want to do is rewrite all of these numbers underneath the radical. So this is going to become the square root of 2 times 2 times 3 times 3 times 3. When we are simplifying, we are not changing the value. For example, 1/2 is the same as 3/6. The value does not change. It's just one way is a simpler way to write the expression. So this number is equal to this number. But I can simplify this more. When I have a radical, remember I'm asking myself, what times itself? So I'm going to look for pairs here. 2 multiplied by itself. 3 multiplied by itself. When you have a pair, you bring them to the front. They're going to leave the nest. So now these two become 1 on the outside. So this is 2 times 3 square root whatever is left over, or the 3 inside the radical. I want to leave this as neat as possible. All of this is multiplication, so I can just rewrite that 2 times 3 as 6 square root 3. And this is my final answer. Let's do that again with the square root of 490. So let's break that down. I have 49 times 10. 49 breaks down into 7 times 7, and 10 is 2 times 5. So here are my little leaves of my factor tree. I'm going to rewrite them up here underneath my radical, and that becomes square root of 7 times 2 times 5. Now I'm looking for pairs of numbers. I'm specifically looking for pairs because that's what a radical means, or to find the solution to a radical is asking us what multiplied by itself gets me that number. Well, 7 multiplied by itself is a key step in that, so I can pull that 7 out to the front. This becomes 7 times the square root of whatever is left over, which is 2 times 5. But let's go ahead and combine that, so now I have 7 square root 10 for my final answer. All right, so this is just breaking something down using prime factorization. What if the problem has addition or subtraction in it, though? So this is how I meant this is going to be extremely similar to variables. So when adding and subtracting radicals, you have to make sure that the radicals match on the inside. What I mean by that is this. This is radical 75 and radical 27. These do not match, so I'm not able to add them. But I can see and check if I can make them match. So let's do that. Let's see if I'm able to make them match. So we're going to simplify these similar to how we did with the prime factorization. So 75 breaks down into 25 times 3, and then 25 is 5 times 5. 27 is 3 times 9, and then that's 3 times 3. So if I rewrite both of these, just down here below, this gets me square root 5 times 5 times 3 plus the square root of 3 times 3 times 3. I'm continuing to simplify, and I notice that I have a pair of 5s in the first one and a pair of 3s in the second one. So I'm able to pull that out of each one individually. I'm going to pull a 5 out of the first, and that gets me 5 square root 3 plus, and then I pull a 3 out of the second, so 3 square root 3. Now here's what I want you to notice. If this were to say 5x plus 3x, we would just add them and say 8x. That is the same thing for radicals. Because this 3 and this 3 match, I'm allowed to add them, and I get 8 radical 3 for my answer. Alrighty, let's do that again with this next example. This next example, I'm subtracting two things. So when I'm subtracting, I still need the radicals to match. Currently, they don't, so let's see if I can get them to match. 28 is 4 and 7, and 4 is 2 and 2. So this is going to reduce to 2 times 7 minus, And let's break down 112. 112 breaks down into 4 and 28. That's just one pairing. There's lots of pairings you can do. And then 4 is 2 and 2. And then 28 is going to be 4 and 7. And then 2 and 2 again. So this next radical is going to be 2 times 2 times 2 times 2 times 7. 2 times 2 times 2 times 2 times 7. Now, once again, I want to pull out any pairs to the front of each radical. So that means this becomes 2 square root 7 minus 4 square root 7. If this was 2x minus 4x, we'd just say negative 2x. So just don't worry about the fact that it says square root 7, and instead use that kind of similarly to a variable. It's not the same thing, but it works kind of in a similar way. And we're going to have negative 2 square root 7 for that final answer there. We have one more example. We have square root of 10 plus square root of 15. Let's see if I can make these match. So 10 is 2 and 5. 15 is 3 and 5. So that's the square root of 2 times 5 plus the square root of 3 times 5. What I want you to notice is these do not have any pairs in them, and I am not allowed to share this 5 with this 5. So I'm stuck, and I'm going to say cannot simplify. They cannot be combined because I can't get the radicals to match. So this is adding and subtracting. What if we want to multiply or divide radicals, though? So when multiplying and dividing radicals, you must multiply or divide inside with inside and outside with outside. And you're going to see what I mean by that in just a minute. So in this first example, I have the square root of 25 divided by the square root of 49. Because both of these are perfect squares, I can actually go ahead and simplify those radicals individually. So I have the square root of 25, which is equal to 5, over the square root of 49, which is 7. So I'm going to leave it like that, 5 over 7. Let's look at this next example. I have multiplication. Here is where we're going to have to multiply the outside with the outside and the inside with the inside. Notice how this 3 and this 4 are both outside of the radical, while this 12 and this 8 are inside the radical. That means when I'm multiplying, the 3 gets multiplied with the 4, and the square root 12 gets multiplied by the square root 8. I cannot mix those. So 3 times 4 is 12. Now I put in my radical. 12 times 8 is 96. So notice the 3 and 4 stayed on the outside. The 12 and 8 stayed on the inside of the radical. Now this 96 can be reduced, so I want to start doing that. So what does 96 break down into? It can break down into 12 and 8. We already know that. And 12 breaks down into 2 and 6 breaks down into 2 and 3. 8 breaks down into 2 and 4 breaks down into 2 and 2. So all I did there was write out my prime factorization. Now I'm going to circle on my prime, so I got 2, 2, 3, 2, 2, and 2. Let's rewrite this expression, but now in my prime factorization. So this is equal to, the 12 is still in front. Now I have my radical, if I can get my pen to write. There we go. 2 times 2 times 2 times 2 times 2. So that's 5 2s. And then times 3. Okay. We're pulling out anything we can. So this 2 is getting pulled out, and this pair of 2s is getting pulled out. They go to the front, and remember, everything is multiplication. So this is going to be 12 times 2 times 2, radical 2 times 3. This 2 times 3 did not have anything it could be paired with, so it stayed on the inside. So let's just multiply everything out or together so that it's all one more condensed form. So 12 times 2 is 48. And then the square root of 2 times 3 is the square root of 6. And here is my final reduced answer. For my final example, I'm still using the same properties that I used in this one. I keep the outside number with the outside number and the inside number with the inside number. So a fraction bar means division. I'm going to divide the 8 and the 2 and divide the square root 10 and the square root 2. So what is 8 divided by 2? That is 4, and it's staying on the outside of the radical. Next, I have square root 10 over square root 2. Well, go ahead and write your square root. And what is 10 divided by 2? Well, it's 5. So I'm leaving it in the radical, and we're done. That's as simplified as it can be. We just have one more skill to cover. And then we are done with 8-0 notes. So when the last type of thing that we're going to be doing to radicals is something called rationalizing the denominator. But what does that mean? So basically, when rationalizing the denominator, you are trying to get the radical out of the bottom. So get the radical out of the bottom. And remember, the radical is that little elbow symbol thing, this guy. So in order to get the radical out of the bottom or the denominator, you must simplify the bottom, then multiply by what is left over in the radical. So these are your two steps. By whatever radical is left over. Okay, so let's go ahead and begin with that. Notice how I have a square root in the bottom of my first fraction. I don't want it to be there. So I need to first simplify the bottom. The square root of 2 is already simplified. So I'm done with step 1. Step 2 is to multiply by whatever radical is left over. On the bottom, a square root of 2 is left over, so that means I'm going to multiply by square root 2 over square root 2 for my next step. Now I'm ready to just simplify. So, remember from our multiplication, we said whatever's on the outside gets multiplied with the outside, whatever's on the inside gets multiplied with the inside, so let's do that here. 4, there's an invisible 1 in front of this. 4 times 1 is equal to 4. And then I have square root. And then 3 times 2 is 6, so square root 6. Over square root 2 times square root 2 is square root 4. But the thing is, we know what the square root of 4 is. The square root of 4 is 2. So now I have 4 square root 6 over 2. And because both the 4 and the 2 are on the outside of the radical, I'm allowed to reduce it, getting me 2 square root 6 for my final answer. Let's do that again. On this next example, I need to simplify the bottom. The radical is already simplified. 3 or square root 3 cannot be broken down anymore. So next, I multiply by whatever is left over. The square root 3 is left over, so I'm going to multiply by that on top and bottom. When I do that, that gets me 5 times 1, or 5. 6 times 3, or square root 18. Over 10 square root 9. Now, there are lots of ways that you can approach this from this point. Here's what I want you to notice. We only multiplied together what was on the outside together, and then we multiplied what was on the inside of the radical together as well. That works with division too. Keep together the numbers on the outside and the numbers on the inside. What does 5 and 10 reduce to? That reduces to 1 over 2. What does the square root of 18 over the square root of 9 reduce to? Well, 18 divided by 9 is 2, so I'm going to put square root 2 up top. And there you have it. That's your answer. I kept my numbers lined up. Whatever was on the outside, I simplified. Whatever was on the inside, I simplified that fraction. Let's do one more. Step 1 is to simplify the bottom. Square root 12 is not simplified, so I need to break that down. So that becomes 18 over the square root of 2 times 2 times 3, or that's equal to 18 over 2 times the square root of 3. Now I multiply by whatever is left over in the bottom, so I multiply by the square root of 3 over the square root of 3. This becomes 18 square root 3 over 2 square root 9. But what is the square root of 9? Well, the square root of 9 is 3. So I have 18 times the square root of 3 over 2 times 3. Or all of this is going to reduce. This is becoming 18 square root 3 over 6. 18 and 6 reduce. This becomes 3 square root 3 for my final answer. We will practice a little bit more with this just to give you a little bit more confidence. But if you have questions, please be sure to bring them to me, and have a good night.